Hey guys, hello. I hope you guys are good. Welcome again to this lovely session of Electro-technics engineering. Today, you guys will be focusing on electrotechnics and six. We'll be doing efficiency of DC machines. Um, sorry, I wanted to notify you guys that speed control, I covered it in N5. So speed control in electrotechnics N6 is basically the revision of speed control that is in N5. Guys, also please, guys, do like and subscribe to my channel. Please, guys, also share the channel to your fellow students, as I'll be assisting you in this subject. And this is a trade subject, guys. It's a very important subject in your pursuit for becoming an electrical technician, artisan. It's very important, guys. This subject is a trade subject, so please study with understanding. Okay, guys, as I've said, that the- we'll start with efficiency of DC machines. But before we start doing efficiency or we start doing the calculations, there are a few basics that you need to understand with regards to efficiency. We know to calculate efficiency, we take the power out. Efficiency is the ratio of the power out over the power in. So we are comparing the output power and the input power. That is what a ratio is. It compares two quantities. Okay, that is how we calculate efficiency. That is as far as we know generally. Generally, okay. But something is missing here, guys. We are missing something very important that we're not considering in the previous levels of electrotechnics. That uh, thing that we are missing what we call losses. Okay, we are missing this very important part. Okay, so in in N6, we are going to accurately calculate the efficiency of DC machines because this time around, our values that we'll get will be far more accurate than the previous levels when we're calculating efficiency. Because when we were calculating efficiency in the previous levels, we were not considering the losses. Okay, so that will make our values not to be truly accurate. Okay, so remember, um, power power in can never ever under any circumstance. Sorry, power in cannot equals to power out under any circumstance. Never. We have never perfected 100% efficiency in any way. Even whilst we are talking of Elon Musk, anywhere in the world, we have never perfected 100% efficiency. There will always be losses somewhere. Okay, this is due to what? Losses in the machine. Okay. I want to break down, guys, now that I've introduced this concept of losses. Now I need to break it down to you guys. But okay, what losses are we talking about? Okay, let me break down these losses. let me break down these losses for you guys. So we are talking of losses in DC machines. Okay, okay. In electrical, there are two types of losses, guys. Uh, let me divide this. There are constant loss. There are constant losses. Okay, and there are variable losses. Variable losses. Okay. So guys, let me start with a constant losses. A constant losses are losses that do not change. They remain constant. That is why we call them constant loss. They are constant loss for that specific DC machine. Okay, so I'm only gonna write down the losses that will. I won't dwell much or dig deeper into losses, but I want to explain the losses that we will be calculating in these calculations. Okay, the first constant loss is the shunt copper loss. Okay. The shunt copper loss is a constant, particularly because the current that is flowing in the shunt field winding. Remember, we are talking of a shunt connected DC machine. Okay, this loss does not apply to a series connected. Please, guys, it says shunt copper loss because the current that is flowing through the shunt field winding, it is constant. It means that this loss is constant because remember, copper loss is a function of the current and what? And the resistance. This is why this loss is constant, is because the current flowing in the shunt field winding is what? Constant. Is what? Constant. That is why if this shunt machine is a motor, it runs at a constant speed. Sorry. If this shunt motor is a generator, it can produce a constant voltage. It's because the current that is flowing through the shunt winding is constant. Um, the last uh, constant loss that I'm gonna talk about, basically, I'm gonna combine these ones into one specific. Okay, that is the ion friction and windage. Sorry, and windage losses. Okay, um, windage losses. What you immediately notice about these losses, guys, they are non-electrical. They are non-electrical. So we have ion losses due to magnetism, friction loss due to the friction because kaloku remember a motor has moving parts, okay, or a generator has moving parts. The electrical machines, generators and motors, they have moving parts. So you will get these losses. That is the ion. This is due to the magnetism, uh, friction and windage loss. Windage loss due um, to the resistance because this thing is what? Rotating. Okay, these are rotating machines. So these are the two constant losses that we'll be talking about. That is the shunt copper loss, ion, friction, and windage loss. Okay, let us go now to the electrical, sorry. Let us go to the variable losses. Okay, the first variable loss that I'm gonna talk about is the series copper loss. Okay, Series copper losses. Series copper losses are variable losses simply because uh, the current through the series field winding is dependent on the current that is flowing through the armature. Okay, so that means the current through the series field winding is not always constant. So, okay, one would ask, why am I putting the armature current? Because remember, in a series machine, the field winding and the field winding and the current through the field winding and the current through the armature are what? Are the same, guys. I series is equals to IA. That is what? For a series, what? A series machine. And this is why this loss is variable, because the armature current is not always what? Constant, meaning the series field copper loss will vary. Okay. Number two, armature. The armature copper losses. Okay, the armature copper losses. Okay, as I've said, the armature current is not always constant. It depends on the load demand. Okay, so this loss is IA squared. Remember, copper loss, anything that is a copper loss is a function of what? Current I squared R. That is why when I'm always specifying copper loss, I'm saying I squared R. Because as much as this is a series, this is an armature copper loss, they are the same in such that they are the function of the current and what? The resistance. Okay, and notice another thing, guys. I don't have a formula for these losses. That is why I will be manipulating, as you'll see when we start doing calculation, to get this loss so that I can fully calculate the efficiency. Okay, that is another variable loss that I will be talking about. Lastly, another one that can be remember the brushes, which is remember DC machines have brushes, which are carbon brushes. Those carbon brushes, because they have resistance, is mean that we will get also what? Copper loss. So the brush copper loss is also variable because the current that is flowing through the brushes is the same as what? The armature current. That is always the case. The current flowing in the brushes is always the armature current, making this loss a variable one. Brush contact copper loss, brush contact copper loss, which is gonna be I A squared R what? B, as I've said, that the current through the brushes is always the armature current. So okay, guys, these are the losses that we are looking at. These are the losses that we are considering in order for us to accurately calculate the efficiency of a DC machine, because practically speaking, we have to consider these laws. Okay, theoretically, we were not considering them. That is theoretical. But on a practical level, we have been perfected 100% efficiency. 100% efficiency. I don't care if the car is a Lamborghini, Rolls Royce, it is never 100% efficient, even though it is built by well advanced engineers. But at the end of the day, there's nothing that is 100% efficient. So we divided our losses into the constant loss and the what? Variable loss. So meaning, guys, when I'm doing calculation, if I calculate this constant loss, they will never change. They will always be that value. The only losses that will change that I will have to calculate again are the what? Are the variable losses, guys. Okay, guys, and now that I've introduced to you this concept of losses, of considering losses, uh, let us first look at power in DC machines. And we know that because we know that there are two types of DC machines, that is the motor and then the generator. Okay. Okay. So I'll start with the motor, guys. A motor, we know that it is a electrical machine that converts electrical energy into mechanical energy. Meaning the input power in a motor is what? Is electrical. I have explained this concept many times in the previous ends, in the previous ends, N4 and 5. Okay. Then the power out in a motor is mechanical. Okay. So basically, guys, because this is a electrical subject, we don't have a formula for mechanical power. Okay, even though maybe if you go study mechanical engineering, you will get a formula there, but we don't put it in the syllabus. Okay, we want to focus more on electrical terms. Okay, so guys, we see that power in a what? In a motor is electrical, which is good, meaning which power in, because power in is electrical in a motor, it means we do have a formula for the input power, which is V times IL. But we don't have a formula for what? For we don't have a formula. We don't have a formula for mechanical power. So, but generally speaking, we know that power in is equals to power out plus what? All the losses. Remember, I've said when I started this session that power in and power out can never be equals to each other. This is why. Because of what? The losses. Power in is always greater than power out. So it means for me to calculate mechanical power, in a motor, I need to manipulate here, which is gonna be power out, which is power in minus the losses. Okay, which is power in is what? Power in is V times IL minus losses. So this is how we get what? The power output in what? In a motor. Okay, so how do we calculate the efficiency of a motor? Okay, how do we calculate efficiency of the motor? With by expressing power out in terms of the input, ne? Okay, we are expressing the power out in terms of the input power, because the power out is mechanical. We don't have a formula to calculate. This is how, okay guys, we calculate the efficiency of a motor. We'll be doing so in these calculations. Okay, I'm only gonna write the simplified version of the formula, which is equals to 1 minus losses over the input. This formula, guys, it's simplified mathematically, but it is derived based on the concept of expressing the output power in terms of the input power. Okay, so V times IL, V times IL in a motor, that is what? That is the input. Okay, then obviously I'm gonna have to multiply it by what? 100%, because we are talking about efficiency. Okay, now let us go to a motor. We are done with the motor. Let us go to the generator, guys. In a generator, input power is what? Mechanical. Remember, a generator converts mechanical power into electrical power. Then the output power is what? Electrical. You will see now the tables have turned in this case. The tables have turned in this case. Okay. So meaning which, if the output power in a generator is electrical, it means that the formula for the output power is V times IF. Okay, then we don't have a formula to calculate the input power of a generator. We must manipulate. We know that the input power, so basically, guys, what we are doing, we'll do in this case, we are going to express the input power in terms of the output power. Okay, because we know the formula for the output power, which is input power is equals to output plus losses. Okay, that is always the fact. Input power, anywhere, any course you study in the future, anywhere, input is always output plus what? Losses. So okay, in this case it is already expressed in the way that I want to express it. So it's gonna be, the input power is gonna be output power. Sorry, output power we said is what? V times I what? L. So okay. Okay. Then how do we calculate the efficiency of a generator, expressing the input power in terms of the output? This is the formula that we'll be using. This is a formula that we'll be using, guys. That is gonna be efficiency of a generator will be efficiency of the generator is gonna be V times IL, V times I over V times IL plus the total losses. Okay, you see that V there on top, that is the output, nah? Then this V times IL plus losses, that is the input, but it is expressed in terms of the output. Okay, then times 100%. Okay, so guys, this is how, please, this is how we calculate the efficiency in a motor. Then, if the question asks you to calculate the efficiency, this is how. You just have to calculate your losses first. Then if the question says calculate the efficiency of a generator, this is how you do for the generator. You just have to calculate the losses first.
Thank you guys for watching this first lesson, part one of efficiency of DC machines. We'll be doing more of this session, the swim bend test, the rope break test, and the Hopkinson's back-to-back test. Please guys, like, share, and subscribe to the channel so I can produce you more content like this in order to assist you in your journey in pursuing electrical engineering. Thank you guys. May you have a wonderful week this week, and may God bless you. Way to TVET Engineering.